This is 7.4 on metallic bonds. I'm still here making videos for you guys. Hope these help. All right, so again, let's look at those objectives. Okay, describe how metallic bonds form. Relate the nature of metallic bonds to the properties of metals and identify alloys and their, can't quite read that on my screen, and their uses. Right? We need to be able to define alloy and metallic bond. Right? So a metallic bond is a force of attraction between metal ions and the valence electrons it shares with other ions of the metal. So what happens is when we have, say, a bunch of sodium atoms, right? Here's a bunch of sodium atoms. Whoops. All right, bunch of sodium atoms. They all have those valence electrons, but those electrons don't like to stay put in a metal. So they go all over the place. All of them do, all those valence electrons. So it's like each metal nucleus is surrounded by a sea of valence electrons. Okay? So, why do metallic bonds form? All right. Recall that metals want to give up their valence electrons. This means that their valence electrons move freely. The electrons form a sea of negative charge surrounding the positive ions. Okay. Metallic bonds and the properties of metals. So here's the thing. If I have an ionic substance, okay, and like say sodium chloride, right, and sodium chloride, and sodium chloride, right, and then there's probably a sodium chloride here, sodium chloride here, and so forth and so on. It's a crystal. Remember, ionic compounds are crystals. If I hit this with a hammer, there's my hammer, bam, all right, what's going to happen is I'm going to end up with sodiums next to sodiums, and they're both positive, so they repel each other. And I'm going to end up with chlorines next to other chlorines, and they're both negative, and so they're going to repel each other. And that repulsion causes them to break. Okay, so ionic compounds are brittle because when you hit them, the like charges repel and they break. On the other hand, in a metallic bond, we have a bunch of sodium nuclei, right? And they're surrounded by all these free electrons. So when I hit a metal with a hammer, the sodium nuclei get closer together, but there's so many electrons surrounding them, they don't repel each other. And so metals are malleable and ductile because of the sea of electrons. Right? So let's take a look at some vocabulary real quick. Malleable means it can be hammered into thin sheets. Okay? Ductile means it can be drawn. Let's not say drawn. Let's say stretched into thin wires. Right? And both of these properties are explained by the sea of electrons around the metal ions. All right. Going back here, it's talking about alloys. An alloy is a mixture of metals. So if you melt down some iron and you melt down some gold and you mix them together and let them harden or cool, you have an alloy. I don't know why you would do that, but you would have an alloy. Gold, for example, okay, 24 karat gold, spelled Karat, is supposed to be 100% gold. Symbol for gold, by the way, is AU. All right. 14 karat gold is an alloy. It is 14 parts gold, okay, and 10 parts something else, usually nickel, okay. Now, if it's white gold, they might mix in some silver. If it's rose gold, they might mix in some copper. But the point is, it's 14 parts gold and 10 parts something else. If it's 10 karat gold, then it's 10 parts gold and 14 parts, usually nickel. It might be something else. Again, if it's rose gold, they mix in copper. If it's white gold, they mix in some silver. Okay. Um, so that those are alloys of gold. So there you go. Stainless steel is a alloy of iron and chromium. Right? And then we have some examples of some alloys and whatnot. Let's take a look at the summary. And then I've got one more thing to go over after the summary. A metallic bond is the force of attraction between a positively charged metal ion and the valence electrons it shares with other ions of the metal. Okay? So a metallic bond is the force of attraction. All chemical bonds are a force of attraction. A metallic bond is the force of attraction between the metal ion and the valence electrons it shares. The electrons move freely around the positive ions, which form a lattice-like structure. With freely moving electrons, metals are good conductors of electricity. Why are they good conductors of electricity? Because of the moving valence electrons. The positive ions of metals can also move within the sea without breaking, right? The metallic bonds that hold them together. This allows metals to change shape without breaking, okay? So the positive ions of metals can move within the sea of electrons without breaking. This makes them malleable and ductile. Pure metals may be less useful than mixtures of metals called alloys. Examples of alloys include steel, bronze, and brass. Okay? Now, I promised one more thing. All right, so we've talked about three kinds of bonds. We have the ionic bond. We talked about the covalent bond. We talked about hydrogen bonds too. And we talked about metallic bonds. All right. Ionic bonds are between a metal and a non-metal. Hope you don't mind me abbreviating. Covalent bond is between two or more nonmetals. Okay. A hydrogen bond is between polar molecules. Okay. And then a metallic bond is between metals. Right? An ionic bond transfers electrons. Covalent bonds share electrons. Hydrogen bonds are just an attraction between the polar molecules. They don't really specifically have anything to do with valence electrons. And the metallic bonds kind of share electrons too. The metal ions share electrons. Okay. So if it's non-metals sharing electrons, it's a covalent bond. If it's metals sharing electrons, it's a metallic bond. Okay. What else can we say about these bonds? All right. Ionic bonds are brittle and have high melting points and boiling points. Covalent bonds have lower melting points metallic bonds have kind of high melting points. Ionic bonds conduct electricity when dissolved. That's a V. That's an E. Covalent compounds are poor conductors. Metallic bonds are good conductors. Where ionic compounds tend to be brittle, you hit them with a hammer and they break. Metallic bonds are malleable and ductile. All right. So that's the summary of chapter 7. Now, obviously, there's a lot more to chapter 7 than what's on your screen right now. This is just a summary, and it's a summary of a summary, really. So make sure you read the chapter. Okay. Now we can go back. Okay. Oops, I went too far. We can go back. Look at those objectives. The objective said describe how metallic bonds form. All right, go ahead. Describe. Talk to the screen right now. Pause it if you need to. All right. So I think what I heard you say was that metallic bonds form because there's an attraction between all those free electrons and the metal ions, right? And they attract each other. Relate the nature of metallic bonds to the properties of metals, right? Go ahead and do it right now to the screen. Pause if you got to. All right. So what I heard you say while the video was paused is that metals are malleable and ductile because when they get hit or stretched, the sea of electrons protect the metal ions from repelling each other. And so metals are malleable and ductile. Identify alloys and their uses. Go ahead. All right. So what I heard you say was that alloys are mixtures of metals. They're not a chemical bond. They're just a mixture of metals. And for example, gold is an alloy used in jewelry. Bronze is an alloy used in statues and stuff and metals and maybe even some coins. Um, so there's a couple. And if you go back to the end of the lesson right there. All right, girders of this bridge are made of steel. Steel is a alloy, and then a blacksmith shapes a piece of iron. Okay, um, probably making an alloy there too. All right, so there we go. Again, I hope these videos help. I'll see you Tuesday after the Halloween break, unless you're watching this some other year other than October 2022. I can't click on the erase thing. So, all right, I'll see you next time.